Welcome, Rohas. Thank you for joining us today.
My pleasure.
Yeah, you can take over from here.
Share my screen. I hope it's visible to all of you.
Yes, it's visible.
Awesome. So let's get started straight away. So if you have a look at the Bitcoin white paper, it's very important to notice that right in the beginning, it very clearly says that this is a peer-to-peer electronic cash. And that's the reason, when we hear so much about centralized exchanging, allowing people to buy and sell Bitcoin, and Bitcoin being talked about as a medium, a store of value, that actually doesn't make sense because it goes against what the white paper started out to do. The white paper started out as a peer-to-peer electronic cash, and cash is something which you use as a medium of exchange. But anyway, let's get a little deeper into it. So when we start with the abstract of the paper, one of the first things that we come across is this concept called double spending. So the most important technical innovation of this white paper was to prevent double spending. So let me first explain what that means. Now, when we take a look at paper currency, right? If you have a currency note in your hand, you cannot spend it twice because the moment you spend it once, the note is gone out of your hand. But when we talk about something which is virtual, so you could take any kind of a file and then copy paste it and make 100 versions, send it by email to 100 people. So before Bitcoin came in, we were not able to have an electronic coin because we did not know how to stop double spending. And that is where Bitcoin came in with this innovation that even though it's an electronic coin, it cannot be spent more than once. So if I have a particular amount of Bitcoin and I give it to you, I can no longer spend it again. Now only you can spend it. I hope that part's clear. If you guys have any questions, you can feel free to post them here. Another very important thing that we've got to look at. So I'll read out some small sections of the white paper and then I'll go deeper into it. So don't worry if it doesn't make sense right now. It'll become clearer. Now, one very important thing to understand is that completely non-reversible transactions are not really possible because financial institutions cannot avoid mediating disputes. So what the Bitcoin white paper was talking about was that conventionally speaking, you do not have non-reversible transactions. Almost all financial transactions are reversible because there may be a chargeback on a card or there may be some kind of a dispute. And there is a company in the middle, a bank or an institution, which could reverse the transaction. But this cost of mediation increases transaction costs. And secondly, that the amount of trust that is required changes. So merchants must be wary of their customers, hassling them for more information than would otherwise be needed. And a certain percentage of fraud is acceptable. You don't really have a choice. These are the kind of problems that Bitcoin wanted to solve. So one of the most important things, and that's where I'll read out this sentence to you, is that the white paper proposes a solution to the double spending problem, which we just spoke about, sending the same coin twice, using a peer-to-peer distributed timestamp server to generate computational proof of the chronological order of transactions. Bear with me if this sounds complicated. I'm going to start clearing it out very soon. The system is secure as long as honest nodes collectively control more CPU power than the cooperating group of attacker nodes. So if you've ever heard of the concept of a 51% attack, where more than 50% of the miners become rogue and they're trying to break the system, well, that's what they're actually talking about here. As long as the honest nodes control more CPU power, so 50% plus a little, you are not really worried about an attack on the system. Now, the definition of Bitcoin or any electronic coin is also mentioned in the paper. It's a chain of digital signatures. And that, I think, becomes the most important issue. And we're going to talk about what a hash is, what public keys are, and how do you verify these signatures, right? So I've made a second. Okay. So first step, let's quickly understand what a hash means. So suppose we were to take a word like Sanya in all small letters and run it through this mathematical function called a one-way hash function. This word Sanya is being converted into this 64 character phrase. Right now, while it may look to you as a very jumbled up phrase, it's actually just a number in the numbering format hexadecimal. If I convert that into all capital letters, I can see that even though the word is the same, the hash has completely changed. Similarly, when I put the first letter capital, the hash again changes. So even a tiny change in the input results in a completely different output. And even if the input was, say, a 100-page PDF or a 1,000-page Word doc, the output would still be 64 characters because we are using what we call as the SHA-256 hash function. If we use some other one, like say we were using MD5, it would be 32 characters. So while the number of characters is the same, obviously the number keeps changing. So as soon as you change the input even a little bit, the output changes. So to summarize what a hash function is, a hash function is a mathematical function, takes any electronic record, could be an email, a video, PDF, anything, gives you a fixed length output, for example, 64 characters. Now, if the information is changed in any way, even a comma is changed in a 3,000-page document, a different output is produced. So many times when you're downloading software, you may be hearing about concepts like checksums. Well, basically, checksums or hashes, they allow you to figure out whether a particular software file has been tampered. Even a tiny tampering would immediately be caught because the hash would be then totally different. And while it is very easy to calculate the hash of anything, reversing the concept wherein I give you a hash and I say, what was the original? Well, that is considered computationally infeasible. I hope all of this is clear. If you guys have questions, feel free to put them in the chat. Now let's quickly understand the two types of cryptography because that's also really critical here. One is what we call as symmetric cryptography. So just like you take any normal lock and you use a particular key to lock it and the exact same key to unlock it. So that's what we call as symmetric, where you could take any plain text, it could be a message, it could be a file, you encrypt it using a key and you decrypt it using the same key. So simple, that's called symmetric. However, if you encrypt it using a particular key but decrypt it using a different key, then we call it asymmetric encryption. So kind of like, if you talk about a bank locker, right? So when you want to open up the bank locker, you need two keys, yours and the bank manager's. But when you're locking, you just need one key to lock it. So this asymmetric kind of works in the same way. Each person would have two keys, a public key and a private key. So I would distribute my public key to everyone, but I wouldn't give my private key to anyone. So if you wanted to send me an encrypted message, you would lock it up using my public key, and only I would be able to figure it out because I have my private key and I can unlock the message. I hope it's all clear. Like I said, you have questions, feel free to put them here or jump on the video and you can ask me your questions. Now, digital signatures is an application of asymmetric. So here what we do is we take an original message and we digitally sign it using our private key. And once I've signed it using my private key, anybody in the world who has my public key can verify whether or not I've actually signed it. So if you ever filed your income tax returns online, for example, you've actually ended up using digital signatures, and for which you would have taken something called a digital signature certificate from a government authorized certifying authority, so that anybody in the world, including the government, can verify whether or not you've actually signed that document. So that's how digital signatures work. Now, this is what they actually look like. So you're seeing a lot of alphanumeric stuff, but they're all actually just numbers, right? So this is an example of a private key. Now here we're talking about an algorithm called as ECDSA, which is elliptical curve digital signature algorithm, very, very popular today. It's the algorithm for digitally signing or for creating these signatures and key pairs. So this is what a private key could look like. This is what a public key could look like. This would be, say, the data that you've signed. So this is a quote by Bruce Lee. Now, when this particular data is signed with this particular key, this is what you get as the digital signature. However, every time that we change the private key or we re-sign, the signature will look different because even the timestamp is kind of put into this when it is finally calculated. But as long as I've signed it using my private key, anybody having access to my public key can verify whether the signature is valid or not. Now, let me show you a simpler example. So let's say we use one of these freely available GPG kind of software. If I wanted to create a key pair for myself, I would just enter my name and email address, and I'd give some comment what this particular key pair is for, because I can open as many as I want. And then I can choose which algorithm I want. So RSA, DSA, these are some of the very popular ones. I could even set an expiry date for my key. And then I put a passphrase, which means even if somebody manages to get hold of my private key, they cannot sign till they have this passphrase. So it's like an additional amount of security that we can put in. Now, this is what a public key could look like. So using this particular software, we can see that, okay, this is what a public key could look like. But don't worry about it, because you never in real life have to look at these keys and handle them. It's all handled by the tech. But if you actually export a public key, this is what it could look like. This is what a private key would look like. And now let's say I've got this done up on my system. All I could do is go to any file, right click on it, and choose what I want to do with the file. I want to encrypt, decrypt, sign, verify. I can do that very easily. It's just a click. Once I do that, it asks me, okay, you've got so many keys. Which one do you want to use to sign this particular file? And then it would generate this kind of a signature. And that would be sent along with the message or the document. I would send the signature, and then anybody else would be able to verify it. So it's fairly simple. I mean, if it's, and then the person at the other end, when they get it, all they need to do is right click and see whether it's verified or not. So it would say trusted, not trusted. Very simple to use. Now, the only reason I showed you all this was to understand that no matter how complex all this sounds, it's all pretty automated using mathematical formula. We don't really need to do anything manually here. So the Bitcoin white paper talks a lot about digital signatures, because ultimately that's what an electronic coin is, a chain of signatures, which I'm going to explain to you in more detail very soon. Another very important concept they bring in is of a timestamp server. I'm going to go detailed into that. But before that, we need to understand the most critical part. And that is what we speak about proof of work. And I'm sure all of you have heard about the concept of proof of work. So in the Bitcoin white paper, they said that to implement this distributed timestamp server on a peer-to-peer basis, we are going to use something called a proof of work system, similar to what somebody called Adam Back had invented. He invented something called Hashcash, and I'm going to show you what that actually looks like. Now, this is the most difficult part of the white paper, so I'll try to explain it in as simple as language as I can. We've understood what hashes are, right? Now, let's take an example of an email service, right? So let's say we want to use this so-called proof of work thing to authenticate emails, or rather to make sure that a spammer is not sending out too many spam emails. So what Adam came out with the concept was, suppose we make the spammer pay for every email, and obviously not paying in terms of cash, but paying in terms of computational power, which means that for every email that the spammer is sending, the spammer is proving that my system has carried out some work. It has done some kind of calculation. Now, doing the calculation requires a lot of energy and time. However, verifying it is like a micromillisecond. So let's say we decide to use a system where we take the sender's email, which in this example is sanya@example.com. We put a separator in the middle, it could be any symbol. We put the receiver, which is samira@example.com. Then we put the timestamp. So we are representing the time in which this email has been sent in a timestamp format. We are using the Unix timestamp. Now comes the fun part. After that, we put in a number which we call as a nonce, and we start with 0. We take this entire string, we run it through the hash function, and then we calculate the hash. But we've made a rule, which you can see here, point number 2, that the hash must begin with 4 zeros. So randomly we've taken this, that there must be 4 zeros. So when we look at this first one, does it look like 4 zeros in the beginning? No. So the computer realizes 0 is not a valid nonce. So it goes to the next step and it goes to 1. It again runs this entire thing through the hash. Now when we use it as 1, does it give us 4 zeros to start with? No. we keep increasing this nonce till we reach a number, which in this example is 161,000. And for this number, when we take this entire line and we hash it, the hash now begins with 4 zeros. And that now tells the system that this particular nonce is valid. And now we can, sorry, and now we can actually send out this email along with this nonce. The receiver will just verify whether this nonce actually fits the equation properly. So the receiver is just going to take a millisecond on it. But we did a lot of calculations because we started with 0 and we went all the way to 161,000. But the receiver only checks 161,000. That's how this basic concept works. If there are questions, you can put them in. I can already see a couple. Let me just quickly look at them. Can you revisit the problem of malicious nodes and the problem of collusion, which can theoretically creep into the network? I'm going to be coming to this soon. So once I'm done with this entire proof of work thing, we'll come back to this. Another question is this the only kind of work? So in a proof of work system, the work that you're doing is calculating this nonce. And you calculate the nonce by running these different numbers and getting a hash which must meet a particular formula. And I'm going to go deeper into that. So yes, this is the only kind of work you need to do. Now, one thing we must understand is there are unlimited number or an infinite number of nonces that exist for any given string. However, you just need to find one. It doesn't matter whether you find the first or the 10th. You just need to find one nonce that fits and send it along. I hope this part's clear. Now, to give you an example, if this particular string, which we took right now, for which I said 161,000 is a valid nonce, if I continue calculating, I'll realize that the next valid nonce is 202,312. That also begins with 4 zeros. Similarly, I've already found 5, 6 of them here. And if I continue to do this calculation, it is going to go on forever. There are an unlimited number of nonces that are going to satisfy the requirement of our algorithm. Hope that's all clear. I don't see any other questions. Now, let's say we did this email system. And now how would it work in real life? So what would happen is every time that email is going, in the message header, we would have this nonce put in, and then it would be verified by the receiver. And just like if you look at your Gmail today and you go to view original, whenever you open up your email, you look at the headers, you will see something like SPF, Sender Policy Framework. You will see something like DKIM, Domain Key Internet Management, which is basically ways to verify that this is not a fraud email or not phishing. All that would happen is below that you would have proof of work, and then it would say, okay, it's passed with, say, this particular nonce. Of course, this didn't happen in real life. Although this system of proof of work was invented to reduce spam, it never really took traction. Not many email service providers integrated proof of work into their email systems. But Bitcoin came and took it into the electronic coin system. And that's the reason we're talking so much about it right now. Now, let me show you how the same proof of work is going to be used in the blockchain. So blockchain is basically a term for a network, and Bitcoin's blockchain was the world's first. Let's try to understand how it does. But please understand, I've kind of simplified a lot of this. So a few things don't really exactly happen this way, but from an understanding point of view, this is fine. Now, every blockchain, it starts with a block which we call as block 0. We call it the Genesis block. Now, it's kind of like, when the universe was created, you had the Big Bang. Now, at the time of the Big Bang, the laws of physics did not exist. And then as the Big Bang started to propagate, that's when the laws of physics came. It's the same way in a blockchain. The first block, this block 0, does not follow the rules of the blockchain. The creator of the blockchain can hard code things into it or can do whatever they wanted into that block. But after that, every single block is going to follow the rules which are laid down. So for sake of understanding, let's presume that right now we are at block number 17. So we started with 0, 1, 2, 3, we've reached 17. A block can be divided into two parts. What you see on top is what we call as the header. And this could be called as the body of the block. Now, in the header, we have four things. One is hash of the previous block. So these four things that you see here of block 16, these are run through the hash and this hash is generated and it is stored by block 17. That's the reason every block knows which is the block that came before me because it knows the hash of the block. So if anyone tries to tamper it, the system can immediately figure it out because it will know that the hash has been tampered because the header knows the hash of the previous block. That's the first one. The second is the timestamp. When was this block mined? So mined is basically, you could say, when was the nonce of this particular block calculated? So we can say that's the timestamp. Again, I said I'm simplifying. Now, this is the nonce. We know what that means. But this is a very interesting concept called as a transaction root. Let me explain to you what that means. Now, let's say that in a particular Bitcoin block, so, blocks are created roughly every 10 minutes. So let's say globally, 4 transactions happened at that time. Of course, in reality, many more happened, but then we're talking right in the beginning of the chain. So let's say there were 4 transactions. Now, what the system would do is it would take transaction 1 and 2, concatenate them, and first it would generate the hash of transaction 1, hash of transaction 2, concatenate these, and calculate hash. Then it would take 3 and 4, individually calculate the hashes, concatenate, get you this one. Then it would take this and this, concatenate, rehash. And the system would keep doing this till you finally had one hash left. And that hash represents all the transactions. So if you were to make any modification in even one of these transactions, the final root would not match. And this transaction root goes into the block header. So those are the 4 pieces of information that go into the header. Hash of the previous, timestamp of the current, transaction root of the current, and the nonce. How is this nonce calculated? When these 4 things are put into a line, run through the hash. So here Bitcoin uses SHA. Run through it. The hash should begin with a certain number of zeros. And that certain number of zeros keeps changing. And I'm going to come to that in some time. Now, one thing that you must remember is that a blockchain is ordered and timestamped. That's very critical. The order is critical because it shouldn't happen that I spent something in block 20 but I tried to respend it in say block 21 because the order somehow got manipulated. So the order is critical. It is timestamped. We prevent double spending and we prevent modification of previous records. So these are the characteristics of a blockchain. Right. Let me see if I have a question. Okay. Okay. I don't see another question. Is there any cryptographic method used to merge these hashes? So we kind of concatenate them. So let's say we had an odd number. So right now I told you 1 and 2 is done, and then 3 and 4. So what if it ended at 5? So then we would take 5 twice and then concatenate and calculate. Now let's look at what the white paper talks about when it says proof of work, right? So we said the proof of work involves scanning for a value that when hashed, such as with SHA-256, the hash begins with a certain number of 0 bits. So in that earlier example I gave you about the email system, I said 4 zeros. It was just randomly picked up. But here they're saying the same thing. It begins with a certain number of zeros. And now very soon we are going to see how do we calculate how many zeros it should begin with. I'm coming to that. Then incrementing a nonce in the block until a value is found that gives the block's hash the required 0 bits. So what I just explained to you, that we start with 0 and then we go 1, 2, 3. We keep doing it till the hash starts with a certain number of zeros. And the block cannot be changed without redoing the work. That means once these blocks are being chained, in future, if somebody wants to tamper or change it, there is a way to do it. And the only way is to recalculate the nonce for every single block. So theoretically, it can be done. Practically also in some cases, it can be done, which is why we say the hash power of the network should be really strong. That means a huge number of computational power must come in to prevent unauthorized modifications. I'm going to come to that in some time. Let me just see if there are questions. So transactions 1, 2, 3, 4 are all the same person or global? No, these are global transactions. So it could be like thousands of people around the world, all their transactions are being broadcast. Of course, what happens is, let's say at a particular time before a block starts to get mined, all these transactions are going into what we call as a memory pool. And then the miners get access to these transactions and they can start to mine. Now, the beauty here is you don't actually have to do it in the same order. And as a miner, you can even choose not to take certain transactions. So, in Bitcoin, transaction fee is optional, it's not compulsory. So, a lot of people, suppose they've set zero transaction fee, and some people have put high transaction fee, I'm ready to pay. The miner can pick up only those and ignore the rest. They're allowed to do it, nobody can really do much about them. Secondly, a miner can choose not to take transactions of a particular address or a group of addresses. We call this a censorship attack, but they can do it. So those are some of the interesting possibilities. Then to compensate for increasing hardware speed and varying interest in running nodes over time. So when the white paper was written, the author realized that over time, as more and more people get into the picture, you need more and more hardware. People may or may not be interested in running nodes. So how do we motivate them, right? So what do we do for all that? And how do we make sure the system doesn't really go bust? So the proof of work difficulty is determined by a moving average, targeting an average number of blocks per hour. If they are generated too fast, the difficulty increases. So suppose, suddenly there's a huge amount of computational power coming in and blocks start to be generated very fast. Now on Bitcoin, the average is 10 minutes a block. For whatever reason, the creator decided to go with 10 minutes. Now, suppose the system realizes or the chain realizes that blocks are happening in 5 minutes. The difficulty level will be increased so that the block generation speed goes down. On the other hand, if it's taking too long to generate blocks, the difficulty can then be reduced. So the system automatically does this. And I'm going to go deeper into how exactly that is done. Vinay wants to know what censorship attack is. So, from this memory pool, when the miners pick up transactions, they can choose to not pick up transactions belonging to a certain bunch of addresses. That is called censorship, where they've decided not to pick it up. Right? Now, this term difficulty is now very important. I'm sure all of you have heard about the term difficulty. So, what is the real meaning of it? So, difficulty means how many times more difficult is it to mine a block now as compared to how difficult it was to mine the first block, which is we call as the genesis block or block zero. So difficulty is measuring how difficult is it to find a hash below a given target. And the target is this number, that number of zeros, that's called a target. And difficulty is this ratio kind of a thing. So the target is a number that the block hash must be below. And I'll show you what it looks like. So for that, let's just quickly understand what hexadecimal is. So as normal human beings, we use the decimal system, right? So we talk 0 to 9 and then goes 10, 11, 12, 13, 14, 15. Computers also use binary, which is 0 and 1. They also use hexadecimal, where you go from 0 to 9 regular, and then you go A, B, C, D, E, F. So the number 500, when written in hexadecimal, is 1F4. The number 1000 is 3E8. So like this, if you just say A, B, C, D, E, F, 1, 2, 3, 4, 5, 6, 7, 8, 9, that is the hexadecimal for this very large decimal. So what I want you to remember, whenever or now on this screen, you're going to see these alphanumeric strings, mentally remember they're just normal numbers represented in hexadecimal. So let's say that the current target is this. It starts with a certain number of zeros. And then you have this alphanumeric string, and then you have a bunch of numbers. This actually is this number. So what we're trying to say that currently the target is this number, and whoever wins a block or mines a block is supposed to find a nonce which results in a hash which starts with these many zeros, which also means the hash is below this number. Or I mean, this is one of the valid hashes. So as you can see, this number is smaller than this number. So the work that a miner is doing is trying to calculate these nonce and trying to be the first person to do it, because the first miner to do it would immediately broadcast to the network saying, I found the answer. Everybody else could verify the answer. And if it's valid, they measure it like this, that, okay, this is the target. This number is below the target. It means they can accept that block and they can then start the next. And the miner who did this block then gets the reward, which comprises two things: a certain number of new coins that are generated every block, and the transaction fee of all the transactions. So when Bitcoin started, it was 50 Bitcoins per block. Then every approximately 4 years, this number goes to half. So 50 became 25. So 50 became 25, then 12 and a half, then 6.25 currently. This number will keep going down by half every 4 years till the year 2140 AD, which is more than 100 years to go. By that time, because of the halving, the block reward will become zero. The total number of Bitcoins in the world would be 21 million, and no new Bitcoins would be created because the reward would become zero. And that's why you must have heard that Bitcoin has a fixed supply of 21 million. This is how it actually goes. So from the first block onwards, 50 were created. 4 years later, 25, then 12 and a half. That's going on till it reaches zero. And by then, 21 million would be done. Now, how often is the difficulty adjusted? I told you whether too many blocks are coming on average or too few are coming. The system adjusts this every 2016 blocks, which is approximately 2 weeks. So in the blockchain world, we don't use conventional time. Everything is measured in terms of blocks. So for example, when Ethereum's ICO came out, they did not give you a fixed time when the ICO would start and end. They give you a block number saying when Bitcoin's block number is this, our ICO begins. So in the blockchain world, we measure time in terms of blocks. And on an average in the Bitcoin world, a block is 10 minutes. However, that's not a rule. It could be much more and much less also. So the target is readjusted every 2 weeks approx, 2016 blocks, and average is trying to be maintained at 10 minutes a block. Higher difficulty means a lower target value. All clear, I hope. Now, a very interesting thing comes in is that what are the steps to run the network? So step one is new transactions are broadcast to all the nodes. So I'll give you an example. Several years ago in Bangalore, there was this coffee shop I used to go to. When you enter, he would ask you, are you going to pay by Paytm or Bitcoin? Now, if I said Paytm, they would first give me the coffee and let me pay later. But if I said Bitcoin, they would ask me to pay first. And the reason is very simple. A Bitcoin transaction can take up to 60 minutes to be confirmed, so to say. Because even though in one particular block, the transaction has gone through, we wait for 6 confirmations. Approximately every 10 minutes, we get one new block. So we wait for 1 hour and then we say, okay, you know what, the transaction would have gone through. But traditional payment methods happen in seconds, which is why if you said Bitcoin, they'd say pay first, then go in, because they know it's going to take them an hour to figure out whether your transaction went through or not. So now let's say I went to that coffee shop and I paid using Bitcoin. So that's a new transaction. It is broadcast to all the nodes through this memory pool. Each node can collect these transactions into a block. Each node now starts working to find the proof of work, which means to find the nonce. When a node finds a proof of work or finds that nonce, it broadcasts it to all the nodes, saying, this is the block of transaction, this is the order, this is the nonce. Nodes can accept the block only if all the transactions in it are valid. That means they have been digitally signed by the person who controls a particular address. So, every address in any blockchain will have a private key associated with it. It's been signed with that, the transaction is signed, and the public key is used to verify that. So that's something that they're going to check, and only then they would accept it. Vinay says that from the coffee example, isn't this brute force logic of antitrust the reason that it is used more as an inflation hedge or no, actually, you have a good point. So in Bitcoin also, a lot of innovations have now come in. So that's where the Lightning layer and the liquid protocol come in. So now we have something called a layer 2. So when Bitcoin first started, we didn't really have this. But when El Salvador went and made Bitcoin legal tender, You can walk into a McDonald's in El Salvador and buy a burger using Bitcoin. Oh, obviously, they cannot wait for 60 minutes. They cannot wait, so pay so much transaction fee. So that's where, suppose this is the Bitcoin layer, and on top now you have the Lightning Network. What happens is 10,000 transactions could get bundled on this layer 2 and then hit one peg in Bitcoin. So now the transactions can actually happen in milliseconds. So this Bangalore problem, which is why I mentioned, was several years ago, not anymore. So in fact, even on Ethereum, if you've heard about things like Polygon, they're doing the same thing. Because again, Ethereum is slow and expensive, you have an L2 which makes things faster. Same way, Bitcoin also has an L2. I hope that clarifies your doubt. Nodes express their acceptance of the block by working on creating the next block in the chain using the hash of the accepted block as the previous hash. So as I told you, every block knows the hash of the previous one. So let's say 50 of us are mining. I succeed. I immediately broadcast to all of you. These are the bunch of transactions. This is the nonce. You check, everything makes sense. There's no double spending. All the transactions appear to be valid. You accept it. How do you accept it? By going to the next block and taking the hash of my block into your next block. That means I will now get the reward. But of course, I cannot spend it immediately. It waits for a certain number of confirmations, and then I can spend that block reward that I want. And then nodes always consider the longest chain to be the correct one. Now, this is where something very, very strange also comes into the picture, and I'll kind of explain it to you. So I have a question for you, and I'd like you guys to answer it in the comments with a yes, no. Is it possible today that somebody creates an alternate chain for Bitcoin? Now, Bitcoin's been running since about 2009. So we've got, I don't know, thousands of blocks that have happened. Is it possible mathematically and theoretically and practically to today generate a parallel chain which is longer than the actual current one and it actually overrides it? Do you think that's possible today? Anyone wants to take a shot at it? Just give me a yes or no. So, well, the answer very surprisingly would be that yes, it is possible. So, what Bitcoin really uses is probabilistic proof of work. So, it's not technically proof of work. When you say Bitcoin is proof of work, that's not technically correct. It's a version of proof of work called as the Nakamoto consensus, named after the person who invented Bitcoin or wrote the white paper. So, today, if you had access to a super fast computer, which could calculate nonces faster than the conventional blockchain system today, you could actually replace the blockchain with a new one in which you could do all sorts of weird transactions. That's possible. So, well, quantum computing is not really there yet, but if it does come into the picture in future, that's the worry. But you know what? If quantum computing comes in, we have bigger worries. All the military banking conversations of the world come under threat. Bitcoin is very small in comparison to that. But yes, theoretically, it's possible. And I want you all to remember this. Bitcoin is not pure proof of work. It is probabilistic based proof of work. New transaction broadcasts do not necessarily lead to reach all nodes. So, because you know what, there are so many nodes, nobody knows at any given point of time for sure how many nodes exist. Because there's no rule that every node needs to be connected to every other node. So it's possible I'm running a node which is down for 3 hours and it suddenly pops back up again. So at any given point of time, it's possible your transaction went to only 30% of the nodes. Any of that is possible, right? Another very interesting concept is what we call as the incentives. So by convention, the first transaction in a block is a special transaction that starts a new coin. So basically, you know, I said that 50 Bitcoins that you get as a reward. So that's like an incentive for you to run nodes. The reward that you get gets noted in the chain as the first transaction, also called as the coin-based transactions, not to be confused with the crypto exchange in the US, which is also called Coinbase. I mean, they've taken this name from this particular terminology. And of course, CPU, time, and electricity are the things that miners put in. And in return, they get these free coins and they get transaction fee. That's how it works. So it's also presumed that this transaction fee and the new coins is the incentive that is going to encourage nodes to stay honest. that, you know what, if you try to break the system, Bitcoin value goes to zero, you end up losing because your coins then become worthless, right? So in fact, here it says that if a greedy attacker is able to assemble more CPU power than all the honest nodes, that concept is called as a 51% attack. And while Bitcoin, to the best of my knowledge, has never been a victim of that, there is a fork of Bitcoin called Bitcoin SV, Bitcoin Satoshi Vision. And I think it was in 2021 that they went through this attack twice in a year, where rogue power was more than the honest power. And yes, a lot of problems did take place. But this doesn't really happen to Bitcoin because the hash power is extremely large. So to carry out this attack on Bitcoin would require such an enormous quantity of computational power. No one's been able to do it yet. Not that it cannot be done, but it's not happened yet. Hope that part's clear. Now, if you remember when I was talking to you about those hashes, we take those transactions and then we hash it and we concatenate. Well, that concept is called as a Merkle tree. So I'd explained it to you. I just hadn't given the term because we hadn't come to it yet. That is called as the Merkle tree. So this transaction root, which is in every block header, is called as the Merkle root. Let's see if there are any other questions. Okay, so someone says that does this eventually get represented on the ledger since more blocks have been added? So that's a good question. So basically, is it possible that if your transaction has been broadcast or is just not been included in the block? Yes, that can happen. And sometimes that can be for a very, very long time. I mean, I haven't heard of a transaction which has never got included, but yes, it can definitely get delayed tremendously, which is why it's always recommended that you optionally put some transaction fee, right? So now I'm giving you a small basic example that going back to that Merkle root concept, when we really look at it, each transaction basically comprises the quantity, the asset. Now, why do I say asset? Because if it's Bitcoin blockchain, there is only one asset, which is called the BTC. However, let's say we take another proof of work blockchain where people can create their own asset. So that's why I've used the word asset. So it's like how many coins, which coin, what is the receiver's address, what is the sender's address. Basically, that's the critical information, which could then be digitally signed by the sender. And this put together could be considered as a transaction. So like this, there are multiple transactions getting hashed till we finally come to the Merkle root. This is called the Merkle root, and this whole thing is called the Merkle tree. I hope all of that is answered. Yeah, I don't have any other open questions. Then if we go back to the white paper, it says that it is possible to verify payments without running a full network node. So blockchain nodes are of very different types. What we call as a full node is something that has data of every single block from the first day onwards. But all blocks are not like that. We have lots of different kinds of blocks. So lots of different kinds of nodes. Depending upon what they're trying to do, we could have various kinds of nodes. The most important are the full nodes, which have all the data. So a user only needs to keep a copy of the block headers of the longest chain. So like I said, at any given point of time, there are actually multiple chains running. So when transactions are broadcast, it is possible that there are 5 different miners who all found a correct nonce, all 5 broadcasts, but everyone didn't hear everything. So some people accepted miner 1 and started building further. Some accepted miner 2. So again, 6 blocks later, the system looks, sees how many chains are there. If it sees more than one chain, it deletes them and only leaves the longest chain, which is why it can happen that your transaction goes through and an hour later it gets rejected. Doesn't happen very often, but it's possible because of the way it works, which is why it's always the longest chain which is important to us. Another thing I'd like to clarify here, this paper came out in 2008. After that, there have been a lot of technological advancements. So some of the things mentioned in the paper are not really true anymore. Some changes have taken place. Just got 5 more minutes. So if you've got questions, please put them. Till then, I'll continue. Now, verification of transactions is possible very easily as long as honest nodes control the network. Then there's an interesting concept, I don't know if you heard about this concept of UTXO. So blockchain accounting models can be different. So let's say in the real world, you go to a shop and you pay in cash. So let's say you're supposed to pay $10, or let's say you're supposed to pay $3, but you give a $10 note. You get $7 back as change. That is how Bitcoin works. If you've got to make a payment of zero point 0.2 Bitcoin, you cannot pay zero point 0.2. It actually combines certain values, pays a bigger amount, and the extra amount that you paid comes back to you as change, replicating the way in which cash transactions work. However, if you go to platforms like Ethereum, they work like credit and debit cards, where if you have to pay $10, you pay $10. You want to pay $3, you pay exactly three. So whether it's a credit card or a UPI payment, you would pay exact. Bitcoin works on this UTXO model where it's like cash. You pay more and you get the change back, and that goes into a new address. And it's a little complicated, which is why if you look at your Bitcoin wallet, you'll realize there are a large bunch of addresses. So every time that you want to make a payment, you've actually got to specify which address the change should come back to. Now, we don't have the time to actually go into the details of why UTXO is actually a very good way of doing things, but that's just how Bitcoin works. So like I said, these are the two models. So one is the UTXO, which is called the unspent transaction output model. And Ethereum uses what we call as the account balance model. This presentation, I keep it available to all of you, so you can always go through it later. Don't worry about that. So this is kind of an example about how triple entry bookkeeping works in Bitcoin. Again, we don't really have the time to go through this, but privacy is a very important concept here. So when the white paper was written, it was recommended that for every transaction that you do, you should use a different address. So you're never supposed to use the same address for more than one transaction. If you don't follow this advice, then all your transactions can be found out because you're using the same address multiple times. So the Bitcoin white paper always recommends that use different keys for every single transaction. They've also, so if you've looked at the Bitcoin white paper, you'll see that there are some mathematical formulae which are put in there. Now, a lot of people get confused about it. Even if you don't understand the mathematical formula, it doesn't make a difference. All that they're trying to do with that formula, if you look at it, it's simple to understand. They're just calculating probabilities, right? So what they're trying to say is that if P is the probability that an honest node will find the next block, and Q is the probability that an attacker will find the next block, then what you're trying to calculate with this QZ here is what is the probability that the attacker will catch up given a certain number of blocks he's behind. So if the attacker is 1 block behind, 2 block behind, 3 block behind, what's the chances that they can catch up? So if you look at the calculations, yeah, here. So if the probability of an attacker catching up is 0.1 and the attacker is 0 blocks behind you, they're definitely going to catch up. If there's 1 block behind you, the probability now falls exponentially to 0.2. If there are 2 blocks below, it falls down to 0.05. So you realize if the attacker is maybe 10 blocks behind you, the chances of them catching up are next to zero. However, if the probability is higher at 0.3, the numbers completely change. So that's all that those probability numbers are displaying. You don't need to understand it to actually understand the white paper. Let me check. Okay, it's 9:30, so we don't really have time to continue, but I'll share this presentation with everyone. There's actually a lot more, but then we won't be able to cover that today. So if you have questions, we can take them up now. Are there any questions?
So folks, if you have any questions, you can drop them either in the chat window or in the Q&A section.
Okay, so I'll share this presentation with the organizers and you can share them with the participants.
Yeah, definitely. The presentation and all other resources will be available on the Slack channel and on the description on YouTube video as well.
Awesome.
All
Okay,
right.
then.
Seems like we don't have any open questions. Okay, we have one question from Vinay.
So, I'm not sure which is the question. Okay, it's in the open. What about the economics? Observe that both promising commodity theories of. Well, so since today's lecture was more from the point of view of the technology behind it, we didn't get into the economics. But I am doing a live stream on this sometime next week, so you can follow me on any of the social platforms. My name is Rohas Nagpal. There is nobody else in the world with that name, so you can find me very easily. And on every platform, I am ROHAS NAGPAL. So if you attend one of those, I'll be going deeper into how the economics. Any other questions? Why people are not using Bitcoin in large numbers as we use currency? Sure. So I'd say one of the biggest reasons is it's not easy to use it. You need to be quite tech savvy to use it. You need to keep sure your wallets are safe. You need to keep your seed phrases carefully. And another big problem is that the value of Bitcoin fluctuates a lot, right? So when you want to use something as a medium of exchange, you obviously don't want the value of that to change. Uh, Regular currency doesn't really hit that level of volatility unless your country goes into a free fall, which happens in a few countries from time to time. But Bitcoin's value changes a lot. So that's another reason normal people kind of stay away from. I mean, those are some of the reasons why people don't use Bitcoin as much. So there are other cryptocurrencies also which are popular. You have something like a Litecoin, Bitcoin Cash, which are being used in different parts of the world. In fact, recently the Dubai authorities have legally recognized three cryptocurrencies. That's Bitcoin, Ethereum, and Litecoin. So I'm guessing more and more people would start to use that. Bitcoin is already legal tender in a few countries. I'm aware of El Salvador and the Central African Republic. Tron has become legally recognized in some countries also. So yeah, we are seeing cryptocurrency usage increase. Any other questions? Okay.
All right. Seems like we don't have any other questions. Thank you for the amazing session, Rohas. It was indeed very insightful. And thank you everyone for joining in today.
Okay. Bye bye.